Okay, here we go. Let's have a quick look. So you're gonna want to be making sure you bring in your TIE course class for a while, because this is some stuff where why don't you click them all the way close. This is some stuff that you can't really do any other way. This matrix stuff. You have to use it. I mean, you could use another graphing calculator, but I don't think anybody's gonna have a different graphing calculator. So the TI-84 is the one that we're going to have to rely on. Desmos can't handle this stuff. I mean, actually, Desmos could handle this. This is no big deal, right? This is just a linear system. But if you wanted to do a larger linear system that involved more than two variables, it wouldn't be able to help you, right? You can't graph that in Desmos. You can't graph that intersection. But let's do a quick review of how we use matrices, how we use this reduced row echelon form of a matrix to give us an unambiguous answer. So we're going to know there's three possible cases for any linear system, right? Either you're going to get a unique solution where the intersection is going to be a point. If it's a 2x2 system, and by 2x2 I mean two variables and two equations. So the variables are x and y. That's just in the xy plane we get two lines that intersect at a point, piece of cake. If it's a 3x3 system, then that's where we're talking about planes, and it's describing planes in a space, right? And the intersection in that case would look like the example we used last week was, if we have, here's one plane, so we get one equation that's a description of this plane, one equation that's a description of the front wall plane, and then another one that's a description of the ceiling plane, and then the point of intersection would just be the joint up in the corner, right, where they all meet. But once again, that's the first type of solution. It's going to be a unique solution where there's just a single plane, or a single point, right? And what are the other two types of solutions we could get? What are the other two? So, okay, what's that mean? Consistent solution, what's that? Consistent system.
Where
How many solutions would you have? Infinite. Okay. So in terms of a 2x2 system, we looked at that last week. If I have two lines in the xy plane, how could you have an infinite number of solutions? Okay, if they're the same line, sure. Okay, they have to be just different representations of the same line. That's a little easier to recognize. What about in a three-dimensional system where we've got planes? There's some different ways you could get infinite numbers of solutions. What would it be? What's one?
the same plane, or like when the two planes intersect to go along to it, like perpendicular to each other, so they don't stop crossing?
Okay, so what if we had, would everybody agree, and you gotta kind of use your imagination on this a little bit, right? So if we take two planes, we've got the plane of this wall and the plane of the ceiling, right? What does their intersection look like? Line. It's that line right there, isn't it? Right? So if we had a third plane, how could we end up getting an infinite number of solutions? And think what it means to be a solution of a linear system. It has to be a solution of all of the equations in that system, right? So we'd need another way that we could somehow share that same solution, right? It'd have to be, so all the points, everybody agrees that all the points that lie on that line sit in both this plane and that plane, right? They have to. To be a solution, they have to be a part of both planes, right? They have to satisfy both of those equations. How could we get a third plane involved where the intersection is still going to just be that one line? What's that going to look like? What do you think? That's kind of a weird one, isn't it? Right? Can you think how that would be? So I've got the plane of the board, right? And then I've got, and some visual aids here. Let's see. And then I've got paper gap. I'll just use snow boots. I'll use these. These are the ones. First time Scantron's ever been useful, right? So I've got this other plane. There's just a piece of this other plane, right? So they intersect where the paper touches the, everybody get that? How can I get a third one in there? What if we did that? Yeah, what if I did that, right? Does that make sense? They share the same line, right? They intersect along the same line. Everybody agree? Okay. So I could do that. So, but it's a little harder to see with planes. They've all got to intersect along the same line, right? Okay. What are some ways? So that's the other possibility. One of the other possibilities. We can get an infinite number of solutions, right? With lines, it's obvious they're the same line. With planes, it's not so obvious because they can still be three different planes, but still have an infinite number of solutions, right? Now they could be all the same plane. That's kind of boring. And then they'd also have an infinite number of solutions. What's the third possibility? Infinite solutions, or one unique solution, or no solutions. The planes never cross, right? All in the same place. So once again, with lines, that's obvious. What does it have to be with lines? Parallel lines. That's end of story. But with planes, not so easy, right? With planes, they could be three parallel planes, like different floors on a building, right? That's fine. But they don't have to be. They could be, for example, like this plane and that plane and the plane of the other wall, right? There's still going to be some partial solutions where two of the planes intersect. You know, these two intersect here, those two intersect over there, but all three of them never intersect in the same place, right? They could even be like maybe a plane that's sort of diagonal here, so we're looking down a tunnel when we look between the planes. Does that make sense? So like let's say we had one that started down there at that line, and maybe it joined at the other corner of the room up there in the opposite ceiling wall joint, right? So it made like a triangle in cross section. Then each of the planes would intersect both of the other planes, but they'd never all intersect in the same place. And so once again, there would never be, there's no place where all three intersected in the same point. And so there are no solutions of the system. There are some partial solutions, but they're not solutions. They don't satisfy all three equations, right? So that gets a little bit, it gets a little trickier. And there's some ways that we can describe that in math. But I'm not going to do it today, but I might actually, with you guys, I might even give you one kind of like a little bonus assignment where I want you to go back and for the cases where there's no solutions or infinite solutions, you got to describe that with an equation. I'm going to show you a trick. I'm not going to have time to do it. And it's not like I'm going to probably test you on this stuff, but I want you just to see this because many of you are going to go on and do, you'll do that college class that stuff. Class in linear algebra and matrix theory and that stuff. So I want you to have just at least a little bit of exposure to, to what kind of stuff you do like that, right? For today though, let's just do a quick review. Quick review of this stuff. Now what did I do with my pen? I was holding my pen. Oh, it's over there. So these are just the examples that we looked at last week. What if I take this linear system, I've got to put it into standard form where the variables are in alphabetic order, right? So the x term, the y term, and then the equal sign, and then the constant, right? If I put this thing into standard form, here's the matrix representation. If I write the echelon form, right? The augmented matrix where we're going to have same kind of thing. We have columns in the matrix correspond to columns in the system, right? Rows in the matrix correspond to just individual equations in the system, right? So if we do our thing, we input that matrix and then we do our little trick where we do reduced row echelon form of that matrix. So it's going to do all the matrix wizardry behind the scenes. It's going to reduce all the rows. What does this tell us? If you get that answer in your calculator, what's that telling us? Okay, so the first one tells us x equals 3.3. We just round to one decimal place to 3.3, right? Because that's telling us 1 times x plus 0 times y equals that number. What's the bottom one tell us?
Y equals 6.
Okay, rounded to one place, 6.7. So we get one unique solution, don't we? Right? So we end up with the ordered pair. Okay? Okay, what about this? Same kind of thing. So if we put the matrix into standard form and we enter it in our calculator, and we reduce all the rows, and we get this output, what's that telling us? So now, we don't get, let's talk, we kind of rushed through it last week, but the first thing we're always gonna look for is this kind of a look, right? Where we get a 1, and then a 0, and then a 0, and a 1, right? So we're always getting, if I had a very large matrix, what that would look like is, I would get kind of, if I look at the square part of the matrix, if there are 2 variables, I look at the first 2 by 2 part of the matrix. If there were 6 variables, my augmented matrix would be a 6 by 7, right? I'd have 6 different rows for each of the 6 equations. My first 6 columns would be the coefficients of my 6 variables, and then the last one would just be the constants, right? So when I look at my answer, if we ignore that last column, what you're going to get is something, call this the identity matrix. And I don't want to spend a lot of time on that kind of stuff, but if I had a really large system, like say it was I don't want to draw a 6 by 6, say it was a 4 by 4, it would look like this. And then I'd have my last column would be the constants, right? You get that? This is the look we'd have to have here then, because I'd have to have like if I labeled these, let's say our variables were W, X, Y, Z, and then we have our constant column over there, right? The first square part of the matrix, if we got a single solution, a unique solution, would have to look like this, because it would tell us the values of the variable W, X, Y, and Z, right? So we always look for that pattern. If we see that pattern, like we did here, that tells us right away, we know we're getting a unique solution, right? And these are the values of the variables in order, okay? We don't see that pattern here though, do we? Right? We don't see that 1, 1, 0, 0 pattern. So we know it's one of the other two. So we always go to the bottom row to see which one it is. Well, what's that tell us? No. That tells us that's a true equation, isn't it? It says 0 equals 0. How often is that true? Always. So there are an infinite number of solutions. Right? So that bottom row is telling us infinite solutions. Now here's the part that that I maybe want to go just a little further with this group. If we look at that top equation, it's going to give us some extra information. So this is telling us, yeah, there's an infinite number of solutions, and the collection of all those solutions looks like that. Okay, it looks like the equation x plus y equals 3.8. What do you suppose that is? It's math, you're right. But that looks like the equation of what?
Are you recording?
I am recording, thank you.
Doesn't matter.
That's the equation of what? What's that look like if I graph it?
Oh, yeah.
What is that?
A line?
That's a line, right?
Yeah.
That's a line. So that is the line that represents the infinite solutions. The infinite solutions are in the form of a line, and that's the line. Right? Really all that is, these are the same line, aren't they, right? If I were just to simplify one of those, that's what we're going to get back, right? Okay, you see that? Okay? So, I mean, most of the time, like, really at an Algebra 2 level, if we even do this stuff in a regular Algebra 2 class, we stop there. We just want to know there's infinite solutions. But I want you to know that, yeah, if you look above that, the rows above that are telling you specifically, well, what does that actually look like? Infinite solutions, yes. But what does that mean? What's the form of those infinite solutions? In this case, it's that line, right? Okay, what about this one? So once again, we look down here, right? We took a 3 by 3 linear system, and that is not the form that we'd expect, right? It's not a 1, 1, 1, and then the rest of them are 0. So it's not a unique solution. Now if we look at the bottom row, So that box is telling us not a unique solution. It's not a single solution. What's the bottom row tell us? 0 equals 1. How often is that true? So how many solutions are there? None. So there are no solutions. Okay, but once again, what do those top two rows tell us? They actually tell us, and this is kind of the extension for you guys. What's that top row tell us? If we look at this one, that's an equation, isn't it? Right? That's telling us that we've got what? X plus 2z equals 0. Right? Because this is, remember, that's the x coefficient, y coefficient, z coefficient, right? And then there's my constant. So what's that? Well, that's the equation of a line, right? That's a line, but it's not in the xy plane. It's in the xz plane. Okay, so it's not one that's going to sit on the board. It's one that's going to sit maybe in this case, if this is the, right, if this is the x-axis, and that's the y-axis, and that's the z-axis, then it would be this plane right here. The line's going to sit in that plane somewhere. Okay? How about this one? Say it again.
Is it going to be a line or a plane?
It's a line because it only has two variables. Okay? I mean, it's, yeah, does that make sense? Okay, so, how about that guy? What's that telling us? Y plus, so minus, I guess. Z. So what's that? Well, that's going to be a line in this YZ plane, so that's going to be this plane, right? So somehow when these planes all intersect, what's going on is there are these intersections consist of these two lines, but they never all intersect in the same place. Does that make sense? Yeah.
What happens when you have 5 variables?
So 5 variables in terms of what it looks like?
Yeah.
Okay, I knew that question was coming at some point. Let's even just take 4 variables, right?
Not just 3 dimensions.
So, yeah, so 4 dimensions is going to give us a system that we can't represent, right? It's pretty easy for us to make the jump from 2-dimensional system, which we can graph on the board, to a 3-dimensional system. Well, that's just going to add the extra orthogonal. Orthogonal in math's a fancy word that just means mutually perpendicular. So we have room for 3 orthogonal axes in our universe, right? Because we can have 3 lines that are all perpendicular to each of the other. And we can draw the right angles, right? The right angles look like this. There's a right angle. We know that one in the XY plane. But there's also going to be one right there between Z and Y. But then X and Z are also at right angles, right? So each of these 3 axes is always perpendicular to the other 2, right? And so for us to make the extension from X's and Y's to X's and Y's and Z's, it's no big deal, right? Geometrically, we can handle that. Each of these is just a plane in a space. So say we add another variable though. What if we add W to the mix? And now we've got a 4-dimensional system. So that's a problem, because where do you put the other axis, right? Somehow it has to be perpendicular to to all 3 of these, but there's no room in our universe to do that. So you can't physically represent it. We can't geometrically represent it in a way that we can understand, because we don't live in a place where there's room for another orthogonal axis. But in a 4-dimensional universe, there would be. It would be just as obvious to them. They would say, oh yeah, well you just put it there. I mean, and they'd know where it was. It makes sense, but we don't have that space, right? So then you might ask, well, what's the point of that? The point is that the math still works, right? The math still works. The solutions are still meaningful, and we can even look at what those solutions look like. Like the solutions might be, they're going to be the intersections could be 3-dimensional, for example. So they could be things that we could understand as representations in our universe. We just can't understand what the full system looks like, physically. Mathematically, you can. Mathematically, it's easy. But physically, you just can't make sense of it geometrically, right? It's still useful though. In physics, there's lots of situations where you need more than 3 dimensions to make things work, right? I mean, even if you just consider, like if you consider relativistic physics and you want to identify a point in the space-time continuum, like you want to talk about different events, like me snapping my fingers once and snapping my fingers again, those are what we call events in physics. Well, what are the ingredients of an event? You need to know where it happened. So you need to locate it with an X and a Y and a Z coordinate to know the location in space. But you also need to know when it happened, and that's T. That's the time, right? So you can introduce time as a fourth variable. And so you need to be able to do math with that. Well, this math works, right? Or if you want to do, let's say you want to look at things like, you want to look at general relativity. In general relativity, for every direction in space, if you want to account for the effects of gravity, you got to be able to account for you have to be able to account for a tidal stretch and the stretch along both dimensions. You have to be able to stretch things longitudinally and across, perpendicular to longitudinally also. And so what you get is, you introduce these extra 2 degrees of freedom. So you actually, when you want to deal with a gravitational system and explain it mathematically, you don't need 3 dimensions, you need 6 dimensions. But that's okay, the math handles that. The math we're learning now can deal with that, right? The conversation we had earlier about, the warping of space, we probably still need to go revisit that at some point here. But remember we talked about how space is warped by the presence of a gravitational object. It is. Now, I told you it's an extra dimension. Really what it is an extra 3 dimensions. But so to really deal with that, you gotta be able to deal with, instead of just a regular 3-dimensional system, you need to split each of our dimensions up into 2 parts. It ends up being 6. That sounds all crazy, and I know that when people, they think about, like, what's the 4th dimension? Well, there is no simple answer to that. I mean, we need 6 dimensions to understand gravity in the world we live in, right? But that's what these larger linear systems do. Now, not all systems are going to be well-behaved and linear, but a lot of them are, right? And the ones that are really simple to deal with using the same way we're doing it. That's exactly how you would do it if you were studying physics, at the Large Hadron Collider, and you were analyzing a 6x6 linear system. You would put it in your graphing calculator and let it do the math and spit out an answer. The matrices would just look a little bit bigger is all. But the process is exactly the same, right? Okay. So, try that. The names are randomly generated. This is one of my problems that I've just solved all over the place. And it's just, there's like about 500 different names, and that's the one that popped up. How about that? So, so try this. Get out a piece of paper and try this out. So you got to come up with, so there are 3 different questions being asked. So how many variables do you think you need to represent this system? 3, right? As you probably remember dealing with in middle school. Okay, hold on real quick before you jump into it. Thank you. Before you jump into it, just a quick review, right? When you're solving word problems in math, and this is a real thing you deal with, right? A lot of times in word problems, you immediately go to the questions that are being asked to identify what the unknowns are, what the variables are, right? So in this case, we're buying how many pounds of Empire apples, how many pounds of Red Delicious apples, and how many pounds of Golden Delicious apples. So those are probably the variables, right? X and Y and Z would represent the number of pounds of each. And when you're doing this kind of thing, you're starting to organize your work on paper. That's the first thing you should do is declare your variables, right? You got to say what is X, what's X equal to, Y equal to, and Z equal to, and then you can start to build your system, right? Just to keep things straight. Okay? So try this one. Get out a piece of paper. You can team up with your neighbor or your neighbors if you want to. That's fine. Okay, let's at least write down the equation. You guys tell me the equation. Yeah, oh, here we go.
Get the cheap one.
Okay.
I don't know how. Yeah, those ones are off. Get the cheap one.
Okay, equation 1. Look at what they're telling us. They're telling us the cost per pound of each kind of apple, right? And the total amount he spends. How can I turn that into an equation? And here's my X is pounds of Empire, Y is Red Delicious, Z is Golden Delicious. So what do I get?
1.4x plus 1.65y plus 1.65z equals 24.2.
Okay, everybody agree? That makes sense? Okay, let's do something else. So what about this statement right here? If he has 15 pounds total, what's wrong color?
Oh, the X plus Y plus Z.
Oh, what do you know? Okay.
We don't. X plus Y. And then you can add up the.
Okay, one more. So what about this last statement? He wants twice as many Red Delicious as the others combined.
I didn't read that last sentence.
Okay. So we'll pick that up tomorrow.
It makes sense now.